All right. Hello, everybody. Welcome to today's presentation. My name is Pavlo Vlastos. I'm a PhD candidate at the University of California, Santa Cruz, and I'm part of the Autonomous Systems Lab. So I'll be talking today about attitude heading reference system validation. So a brief introduction. We know that we're seeing more and more cases of autonomous vehicles in daily life. Recently, the FAA approved Amazon to use drones to deliver packages to customers. And those kinds of vehicles have a lot of things to consider when we're designing them and building them. Obviously, there's fabrication, manufacturing, system integration. What kind of sensors do we need? What kind of actuators? Are we using a computer or something smaller like a microcontroller? You know, what are the power systems doing? How are they designed? And then from a theoretical standpoint, we have to be able to model that autonomous vehicle, the physical nature of that system. We have to be able to describe mathematically. And that might not be necessarily a vehicle at all. It might be a different kind of robot, a robot arm, a satellite. It varies a lot. But in addition to modeling these kinds of systems, we have to be able to control them. And there's a whole branch of study into, you know, what kind of control can we use. Commonplace, we see the PID controller, but more advanced controllers exist, such as, you know, optimized full state feedback and various other controllers. But part of designing an autonomous vehicle or robot or a system that needs to be able to operate in three-dimensional space and navigate is we have to be able to estimate the attitude and the orientation of that vehicle or of that system. So I'll be talking about attitude, heading, and reference systems, and how can we make sure that they're working? How do we validate that they're working? And I'll be referring to that system as an AHRS for short. So one of the helpful things to understand when we talk about attitude estimation and control, for that matter, of a vehicle is we have to know the vehicle reference frame. And for a robot arm, this might mean that we have multiple reference frames for every link in the arm. For a satellite, it's going to be similar to a vehicle, same for other things like rockets. And in this example, I'm showing an autonomous boat. And we have it doesn't necessarily have to be autonomous for the sake of showing the vehicle reference frame, but I'll explain more about why this specific example is used later. So we have the axes of rotation and the directions of motion. So we have, if you're going up and down, we have heave. If you're moving back or forth, that's surge. And if you're moving side to side, that's sway. That's specific to a boat. And you'll notice that if you've seen vehicle reference frames like this before, for different vehicles, the reference frame is sometimes flipped or has a different orientation. Sometimes you'll have, usually for aircraft, the z-axis is pointing down. But you still have yaw, pitch, roll for all of these vehicles. So when we are measuring the rotation about these axes, we want to find our Euler angles with respect to the inertial reference frame and the vehicle reference frame. And generally we use something like an IMU, or in this case, it's a sensor head. And we have to be able to calibrate the measurements that this sensor head gives us. So for this specific PCB here, this has on board an accelerometer, a gyroscope, and a magnetometer. And it has each of these sensors, it has three, one pointing in each direction of the vehicle reference frame. Now, it gets a little complicated because some of the sensors, such as the magnetometer, might have a different orientation for its frame, where the x-axis is pointed opposite, or the whole frame is flipped, and that's something that you have to account for. Now on the right here, we see that we've collected this sphere of data, and this is accelerometer data that's collected in each axis, and you can plot it in 3D. And if you're doing calibration for these sensors, which you have to do, you'll want to allow the sensor to kind of paint around the sphere and hopefully cover it. And we see there's a lot going on here. We have this dark blue sphere inside, and we have these lighter data points on the outside. And so what's happening is we are calibrating our sensor head. We are collecting a lot of data, and then we're finding how much is it offset from where it should be. So where should it be? Well, ideally, when we rotate the IMU, or the sensor head, we should be able to have this unit norm vector that is always on the surface of that imaginary sphere. And that makes sense, because if we rotate this, we would expect that the direction and magnitude of gravity is going to change in direction, but it'll maintain the same magnitude, and it shouldn't be changing a lot. Ideally, it shouldn't change at all. So we collect this data here shown in blue. This is the pre-calibration data, and we apply a number of different mathematical approaches to correct the data onto the surface of the sphere. And we can find our offsets in the X, Y, and Z axes for those sensors, because they're not going to be perfect. Now, this histogram on the right shows how we are moving the number of data points from being offset by some amount in X, Y, Z, and this is the norm of those of that three-dimensional vector composed of those three elements, and we are able to shift it so that most of the data points are now on that sphere. So this was one of the steps you have to do in order to calibrate your sensor. But once you have it calibrated, you have to have a system to determine your attitude and to determine your orientation. So we have a problem that is intrinsic to the gyroscopes, which is, unless you have extremely expensive gyroscopes, and even then, they're going to drift. And usually it's as a function of temperature, but also it's inherent to when we try to find, our Euler angles, and we're trying to integrate our gyro rates, we're going to accumulate some error because we don't have infinitely fast sampling time. So we have to correct that gyro drift. If they didn't drift, in an ideal world, we would be able to integrate them and obtain exactly our rotation with respect to the inertial reference frame. So this symbol here, we have omega sub y, that represents the vector of gyro rotational rates. And what's happening here is we form a skew symmetric matrix, and then we read in either from our accelerometers or our magnetometers, we take that sensor measurement in all three axes, we generate a rotation matrix depending on the sensor, and we find the error between how much have we rotated with respect to gravity. We project it after scaling it onto that skew symmetric matrix, and then we integrate that. And what this algorithm is doing, this is called the complementary filter, is it is generating an estimate of our rotation matrix, shown here as R hat. Now, you'll notice that R hat is being transposed and then fed back here, and that's where we get the error. Ideally, if our estimate of the rotation with respect to the inertial frame is exactly what our rotation as measured from gravity is, we will have an identity matrix, and we won't be effectively projecting any error onto our rotational rates before we integrate them. But there's always going to be some amount of error, so this feedback loop helps correct for the gyro drift. So there's a bit more math to it. When we do this integration, we can do it a couple different ways, but one of the most effective ways is the what's known as the Rodriguez exponential integration, and that's shown here as a three-term Taylor expansion approximation. And here we have the anti-symmetric projection operator, and that's happening here. So we find the difference between what our sensors measured for the rotation and what our estimate was, and we can project the difference in the form of a matrix onto our rotational rates. And that's, again, that's formatted as a skew symmetric matrix. Once we have this matrix and we've done all of this math, we can then extract our Euler angles. And so that's what's happening here. We can get our yaw angle, our pitch angle, and our roll angle. Now notice here I've indexed these by 1 through 3, but depending on your formatting for a code, this is sometimes indexed from 0 to 2. But the point of all this is this complementary filter is going to be used to estimate the vehicle attitude. And part of that is from extracting those angles. So once we do this and we apply our complementary filter, or perhaps we have a different one, such as a Kalman filter, we have to validate that AHRS. So the complementary filter is part of the AHRS along with the IMU sensor head, and we have to make sure that it's actually working. So we could compare angular rates. We could compare the angles themselves, the Euler angles. So if you have a lot of money, you are able to do this using a rate table. You can compare on each axis. You can rotate a very large, very well-machined gimbal so that you can have your yaw, your pitch, and your roll. And you can find those rates directly with these external sensors in this gimbal and compare them to what your AHRS is doing. And ideally, the difference is 0. Ideally, they are the same. So what I worked on was a validation apparatus that did not cost as much money, but could still be useful for smaller projects that require developing your own AHRS. So here we have a laser cut MDF frame that's holding an IMU, an encoder, and a microcontroller. And what's happening is we are able to measure within just a single axis the roll angle, and we can measure that with the encoder and compare it to the IMU sensor head and the onboard AHRS. So, and this doesn't necessarily have to be onboard. You could also collect all this data and then process it offline too. But we can also rotate the sensor head mount so that we can vary the contribution of these external aiding vectors. And that can include gravity or the magnetic field in this case. Now for satellites, they can use the sun as an external aiding vector, but that's a whole different story. We can talk about that after the presentation. Notice here that there are a couple different ways that we could orient the IMU. We could actually test for the yaw angle. We could test for the pitch angle. And so this can be detached and then placed back on in a different orientation to isolate that axis of rotation. So here's some data collected by this apparatus. In green, you can see the encoder angle over time, and in red, you can see the roll angle from the complementary filter over time. You can see that there's pretty good agreement, and ideally, they should overlap exactly. On the right, we see this is output from the complementary filter and the encoder from the apparatus, and now it's positioned at 90 degrees. So this is highlighting the fact that at 90 degrees, your external aiding vector for gravity is not going to contribute to your orientation estimate because it is now parallel with your roll axis. And that is a good indication that your AHRS is working. If you were oriented at 90 degrees with your roll axis and you saw that gravity was contributing, then you might have a problem with your calculations. So another test we did after applying this apparatus and tuning our complementary filter is we put the system, the IMU, the microcontroller, and the GPS on a small remote controlled boat. And we took some GPS data. One of the measurements that GPS data can give you is called the course over ground angle, or COG. And that is the direction you are going, the angle of that direction with respect to a local tangent plane. This is a very useful measurement to have because we could compare it with the yaw angle over time from the complementary filter. And that's what we see here. In red is the yaw angle from the complementary filter, and in green is the course over ground angle. There's pretty good agreement, but you can see that there are larger errors in some of these areas. However, this was useful to do in order to validate that over a long time, the direction is the same, and that potentially we could use both the course over ground angle as well as the yaw angle for autonomous navigation. Now for a boat, this is relatively simple. For aircraft, where you're dealing with all dimensions, you would have to collect data for each axis, and that can get a little bit more complicated. So I'd like to thank you for listening to this presentation, and I'd be happy to answer any questions at this time. I hope you enjoy the presentation.